Now also to illustrate the third property of the PDF, let's calculate the probability that x is between 1 and 1.25. Nothing magical about these numbers, just numbers that we arbitrarily chose. So the third property says that we need to integrate the PDF over that interval from 1 to 1.25. Over that interval, the PDF looks like this, 2x minus 2. And we integrate that to get this very small probability of 0.0625. We see that that's very small because there's not a lot of area underneath the density curve between 1 and 1.25. Now lastly, let's find a formula for the CDF. So find the CDF, we're going to integrate the density curve from negative infinity up to x. Okay? Now if we choose x to be less than 1, we see that the area to the left of x is 0. And so for any x less than or equal to 1, capital F of x is 0. If we choose x greater than 2, then the total area to the left of x is going to be the area of this triangle, which we know is 1. And so for any x greater than 2, capital F is equal to 1. Now if we choose x between 1 and 2, the area to the left is going to be the area underneath the small portion of this triangle. In terms of integrals, we're going to integrate from 1 to x, and then this is our density function in terms of t rather than x. And we integrate that using the fundamental theorem of calculus, and here we get a formula for the CDF for x between 1 and 2. Sketch a graph of this CDF. And we see that for x between 0 or less than 1, the value of CDF is 1. For x greater than 2, the value of the CDF is 1. And then for x between 1 and 2, the shape of the CDF has the shape of this parabola described by this x squared minus 2x plus 1. So next, let's point out some important differences between a PMF for a discrete random variable and a PDF for a continuous random variable. For a discrete random variable, we use the PMF to calculate the probability that x took on some particular value. So for instance, f of a, where a is some number, is by definition the probability that x equals a. Now if a is in the range of x, then this probability is positive. If a is not in the range, then this probability is 0. So we use the PMF to calculate the probability that x takes on some particular value. However, for a continuous random variable, if we tried to calculate the probability that x took on some particular value a, in terms of intervals, that's the probability that x is between a. And so by property 3, to calculate this, we would integrate the PDF from a to a, and from calculus 1, we know that an integral where the lower and upper limits are the same is equal to 0. So this illustrates one important difference between a continuous random variable and a discrete random variable. In a continuous random variable, the probability that x takes on any one specific value is 0. That's not the case for for a discrete random variable. Discrete random variable, the probability that it takes on some particular value can be greater than 0. It also illustrates that for a PDF in and of itself does not give a probability. In order to find a probability, we must integrate the PDF. I could plug in the number a to my PDF and get out a number, but that's not going to be the probability that x takes on that particular number. Probability that x takes on any one number for a continuous random variable is 0. Okay. So again, PMF and PDF are not exactly the same. They're very similar, but fundamentally different. Okay. Our next definition, we're going to define some different terms that are all very similar between a continuous and discrete random variable. So if x is a continuous random variable with PDF f, the mean of the random variable x is denoted mu, or e of x. And to calculate that, we take x times f of x and integrate that over all possible values of x. The variance is denoted sigma squared, or var x. and that's defined to be the expected value of x minus mu squared. To calculate that, we take x minus mu squared times f of x and integrate over all possible values of x. Standard deviation, denoted sigma, is we take the square root of the variance. The moment generating function of x is denoted m of t, defined to be the expected value of e to the tx. We calculate that by taking e to the tx times f of x and integrating over all possible values of x. The expected value of a function of x is denoted e of u of x, and we take u of x times f of x and integrate over all possible values of x. So you see that these terms are all very similar, all identical to what we used with discrete random variables. Their notations are the same. Their definitions are very similar. The only difference is that with continuous random variables we integrate, whereas with discrete random variables we add. So to illustrate this, these definitions, let's look back at this example, this particular PDF. And so first let's calculate the mean. Calculate the mean, we take x times the PDF, and we integrate over all values of x. Again, we only need to integrate over the interval 1 to 2 because that's the only interval for which the PDF is non-zero. And then we can calculate that using the fundamental theorem of calculus to be 5/3. The variance, we take x minus mu, square it, times f of x, integrate over the interval from 1 to 2. Again, we could integrate that out to be 1/18. Now the moment generating function is a little bit more complicated to calculate. So by definition, we're going to take e to the tx times the PDF, integrate over the interval from 1 to 2. Now here the variable of integration is x, so that means we treat t as a constant. And finding the antiderivative here is a little bit tricky. We may want to use integration by parts, but there's our antiderivative. We plug in our values of x, and here we get a formula for the moment generating function. So this could be done by hand, or it could be done using available software. Our last definition is another idea similar to something we talked about back in Chapter 2, and that's the idea of a percentile. So x is a continuous random variable with PDF little f and CDF capital F, and p is a number between 0 and 1. The 100th percentile is a value of x denoted pi sub p, such that p equals capital F of pi sub p. Now this definition is a little bit complicated because we're using this variable p, or pi. Pi does not mean the number 3.14. Pi is just, we're just using it as a symbol here to denote a percentile. Okay? So the idea here is that, the idea is that the percentile is a value of x. It's a value of x such that capital F of that value is equal p. Now in terms of the CDF, it's the area underneath the density curve to the left of the percentile is equal to p. And now the 50th percentile corresponding to p equals 0.5 is given a special name called the median and is denoted m. And then a similar idea is the mode. The mode of a random variable x is the value x for which the PDF is maximized. In terms of the density curve, the mode is the location of the highest point on the density curve. Now there are three special percentiles that we like to point out, that we give special names to. They are the 25th, the 50th, and 75th percentiles, called the first, second, and third quartiles, or denoted P1, P2, and P3, or pi sub 0.25, pi sub 0.5, and pi sub 0.75. So to illustrate how to calculate a percentile, let's look back at this PDF, which we've seen before, and we calculated that the CDF is x squared minus 2x plus 1 for x between 1 and 2. And so let's find the 25th percentile, P1. And so by definition, the 25th percentile is a number such that capital F at that number is equal to P, which is 0.25. Okay? So now capital F at pi sub 0.25 is equal to this. We simply replaced x with pi sub 0.25. And so now what we have here is a quadratic equation. Our unknown here is pi sub 0.25. Think of that as like an x. So we have an x squared minus 2x plus 1. And so we've got an ax squared plus bx plus c. If we subtract 0.25 from both sides, then we have it equal to 0. And we can use our quadratic formula to find the value of pi sub 0.25, which comes out to be 1.5. Or we could use available software to also calculate that value.